Hey, what's going on, guys? Against here. In this video we're gonna be generating the unique position identifier, also known as the hash key, from scratch using the given position that we actually have. So well, before we start, I just want to show you how XORing is working in order to build this sort of a position key. So just a few quick examples on how it works, just in order to give you an idea like what in particular we're supposed to be doing later on when we would be incrementally updating our hash keys within the make move function. So the idea is very simple. So let me just open the terminal in the current working directory. I just want to say make debug, and if it compiles I want to run the BBC binary executable. Okay, so let's assume that we have our position identifier, also known as hash key. So let's create int hash key here. We'll then create this hash key as a global variable that would be defined where the global board variables are defined. But for now, I just want to define this locally. Sorry, it's not integer. It's unsigned lon 64-bit U64 hash, and well, let's initialize it equals to 0 unsigned lon at the moment, like this. Okay, and also I want to print this. So hash key. Okay, and again, like remember that this hash key is the unique position identifier. That's what it serves for. So hash key, and this would be lon hexadecimal. I want to print this in hexadecimal. It's more handy way of doing things. And this hash key here. So now it, obviously it would be equal to 0. But let's say, let's add a new line here. But let's consider, well, you know, like the reason why I'm telling you this, the reason why I'm actually covering this within the video, because it wasn't really that trivial for me when I've learned this Zobrist hashing a couple of days ago. So until it's kind of fresh in my memory, I want to give all of this emphasis regarding how it works. So well, let's say we want to, so eventually we will need to add to our hash key all the pieces and also the castling, the impedance square if available, the side to move, and the castling right. So everything that belongs to the position itself would be represented within this hash key. So this is quite pretty important. And what we can do, we can add it, we can add something, some piece, or we can update the site, or update the impedance, or update the castling. So we can add something to this hash key, or we can remove something from that. And in order to do both operations, we were using the XOR, the bitwise and XOR operator, and that's it. So if we want to add the piece, we need to XOR. And if we want to remove this piece, we need to XOR it again. And this is how it's done basically. So let's try to add this pawn on A2 to this key. So in order to do this, I just want to say hash key bitwise or equals, and now I'm referencing the piece keys that we have initialized in the previous videos. So random numbers there, the two-dimensional array, piece keys indexed by the piece and by the square. So the piece we have is the white pawn, and the square we have is A2. So that's kind of it. So if we now just do this, we have a random number. So this means that only this white pawn is occupying the A2 square. So if we now want actually to remove this, we just XOR it again, and we'll have the hash key equal to 0 again. So we just remove this pawn, and literally the same with all the pieces, and literally the same with the sides. One little trick regarding the side. So side would be XORed only in case if it is black. If it is white, it won't be XORed. So that's another little trick. In peasant would be hashed only in case if this is not if it's not equal to empty square, and Caslin would also be hashed as well. So there would be some additional tricks to hash to incrementally update Caslin within the make move, but that's the topic of the further videos within this series. Well, okay guys, so without further ado, I would actually now like to start and to write the function that would be initializing our hash key, so generating this unique position identifier from scratch. So I don't really need this code anymore. Okay, and I just want to go to the board representation here, and right below this Caslin, I want to create this variable globally. So I call this unique. Well, let's say almost, because you just read the theory for why I call this almost, because there might be some collisions. So let's say almost unique position identifier. Identifier. I hope I did spell the identifier correctly. Sorry if not. So also known as hash key or position key. So just given all the names available to name this variable, and this would be the U64, and I call it hash key like this. So by default it should get initialized to 0 unsigned lon, assuming the GCC compiler, and that's kind of it. Okay, so well, actually we would be initializing this a little bit later on. So now let's define our generate hash key. Well, generate, let's say unique, almost unique position identifier, also known as hash key, from scratch. So building this from scratch, and I want to create the function. Well, what would it be? Would it be U64, because we would be returning the final key. Okay, U64, and call it generate hash key. Okay, so first I want to define a variable holding this hash key. So this is just what is called final hash key, and this would be the U64 final key. It needs to be initialized to 0 unsigned lon. Hold on, I just want to make sure that I said, oh, I didn't say unsigned lon here. Okay, that's fine. Okay, so, and at the very end we want to return the hash key generated hash key. So return final key, and that's it. So now we need to hash all we have, so pieces, and then in peasant square if available, then Caslin bits, and the site if the site to move is black. So I will now show you how this is going to be working. So let's start with the pieces. So first we need to loop over piece bitboards. Well, actually, we do our loop over the piece codes, and we also need a temporary piece holder to get the squares for our pieces on every single bitboard. So just like we did in our generate move function. So temp bitboard temp piece bitboard copy, and this would be U64 bitboard. And again, like don't get confused by this type, because we use this unknown type for both, like for bitboards and to represent our final key, and they are the same but the meaning is really different. So here it's the matter of where exactly the bits are. Well, here it's just the matter of trying to be almost unique. So these are the different things completely. So here we have the pieces, and this is just random numbers, just to give you an idea. So this is the key, and this is the actual position of pieces for a given bitboard. So don't get confused by these types here. Even though they are the same, they serve the different purposes. So let's say for int piece, well, usually I did call this bitboard piece, but now I just want to say this piece, because just to avoid any confusion on indexing the piece keys array with the random numbers. So I call it piece equals to white pawn, piece is less equals than black king, and piece plus plus. Okay. So now we want to initialize piece bitboard copy. So bitboard would be equal to bitboards indexed by the piece. And once we have our copy, we can actually loop over the pieces within a bitboard, just like we've done in the move generator. So while we have any bits on our 10-bit board, we want to initialize piece square, initialize square occupied by the piece. So integer square would be equal to get least significant first bit index from this bitboard. And in order to end this loop one day and not getting into the infinite loop, we need to pop the least significant first bit. So the one that we just found, so bitboard here. Okay, so we want to pop bit and pop it from bitboard, this copy, and add the square like this. So I hope it compiles and runs. Okay, and now just to give you an idea, so let's just try to print f the square. So just to refresh your memory for those of you who maybe didn't watch the move generator video, so square, and just want to square to coordinates, because obviously coordinates, obviously this square is integer, but we want to convert this to human readable coordinates and indexed by the square like this. And also we need to call it, so I want to generate hash keys. Okay, and we should see the list of all the squares. Generate hash key. Oh, it's not. Okay, generate hash key. Yeah, it's single, it's not plural. Okay, and the new line. So supposing our assuming that we have these pieces, so it generates all the from squares for all the pieces. So should have, so starting from the white pawns, so white pawns, then the white pieces, then black pawn, and finally we have this black king on the square of e8. So I hope this is quite pretty self-explanatory. So here we're getting the list of squares to index our piece keys. So now we want to do what is known as hash piece, or well, hash all the pieces actually. So we're taking our final key here. So we're taking our final key and bitwise OR in this, just like I did it before here in the main function. So we're adding these pieces to this final key. So bitwise OR equals, it might be considered like we just adding this keys for every single piece to the final key. That's it. Just adding those pieces. So I want to reference the piece keys, and the first index is the piece that we're writing over right over in here. So starting from white pawn, ending up with a black king, and then this square. So this is, I hope this is quite pretty self-explanatory. And if we now just try to print this, so well, I can actually try to print. I can try print this. So let's say hash key and lon hexadecimal, the new line, and then this generate hash key. So it returns this final key as the value. So this would be just yet another random number, but this random number already contains all the pieces on the corresponding squares, which is quite pretty important. So the next thing to add here, we need to hash, so I don't remember the order, well, probably probably in peasant, then castling, and then the site. Okay, so now let's say if in peasant square is on board, so I can say if in peasant is not equal to no square. In this case, I want to hash in peasant. So again, like by saying hash here, I mean just like to add the corresponding key to our final key, to our final position hash key, position unique identifier. So I just say final key bitwise OR equals, and I'm referencing the in peasant keys, and indexing this by the in peasant square itself, like this. So I hope this is clear. So if it's equal to no square, like in this case, so this number shouldn't really change at this moment. Okay, so this shouldn't change because we have the in peasant square equals to no square. So if I compile around the code, I really hope to see exactly the same, yeah, so see like exactly the same value here, because we don't yet have the in peasant. And later on, I'll play around with the FEN. Okay guys, hold on a sec. I'm sorry, this is, my wife is calling. Hold on a sec. Okay, sorry guys, yeah. Oh my god, now she's writing me something. Oh man. Okay, I'm sorry guys, just she's out for a couple of days. I hope to work on this weekend making some videos, but she's still torturing me for some point. Okay, it doesn't matter really. So I just can't mute the sound because it would turn out as a complete disaster later on. I'm sorry for these details, but okay. So where did we end up? So we have hashed the in peasant. Okay, so the next thing to consider would be to hash the castling. So it's done simply like, so here I want to hash castling rights. Again, like by saying hash, I just meant like I'm just simply adding this castling rights. So I want to say final key bitwise OR equals with castle keys. I hope that's the name. So castle keys, and it should be indexed by the castling rights. So is that castle like this? I don't really remember. So let's try to see if it compounds and runs to make sure. Okay, and now the key is changed because we did add this castling rise. So again, like we would be changing this castling rise, the hash key would get changed accordingly when we'll start playing with our FEN. So just to make sure that this function is working perfectly well. And the very last thing, I want to hash the site. Well, let's say, yeah, hash the site only if black is to move. So that's how it's done, but by other people. So that's kind of the idea. So we just kind of XORing this site back and forth just to represent the the change of the site within the position. So we need simply to say like if site is equal to black. In this case, we want to say that the final key bitwise or equals to final key bitwise or equals to, oh my god, side key. Okay. Sorry guys, I just keep thinking what my wife has actually sent me an SMS, and okay, just try to focus at work. Okay, and again, like this side change shouldn't change this key because we have a side equals to white, so hopefully to have the same key here. And yeah, it seems like we do. Perfect. Okay, so the next few steps to consider now are the following. So I want to generate hash key in the very end of my parse FEN function. So this is quite pretty important thing to consider. So let's search for the parse FEN, and at the very end here, after initializing the occupancies, I want to initialize hash key. So I need to say hash key, which is the global variable, would be equal, we've defined this before, would be equal to this. And now I just want to go to printboard function, printboard, and yeah, here. And I would also like to print this hash key at the very bottom of, so here, just right below the castling rights, I want to print this hash key as well. So let's actually here like print hash key. So printf and just some space, and how we call this hash key, well, let's call it hash key, but again, just I hope you remember that this is the unique position identifier. So hash key, and this would be the long hexadecimal, and then let's make a couple of new lines, and hash key like this. Now let's adjust the layout to make sure, okay, excuse me, conflicting types, implicit declaration. Oh, okay, so this is happening because I need to put this generate hash keys into an appropriate place. So let's search for Zobrist keys. So right over in here. Okay. Okay. Save. So now this should be working, hopefully. Okay, and we have our hash key being initialized. Okay, so from now on, we can go and play around with our FEN. So I just want to take my tricky position and then just paste it here and manually changing this to see how the hash key is changed accordingly. Okay, so first let's try to play around with the in peasant square. So let's say that we'll put an in peasant square to the square of c6. It's illegal in this position, but just to give you an idea like how the hash key is gonna get changed after. So if I just add c6 here, it should change the hash key. Okay, the hash key has been changed, which is good. So this works. Okay, let's move further on. So now if I would be, so this is the initial key. Okay, so now if I would be changing this castling rights, it should be changed accordingly. Okay, did it change? Yeah, it did change. So no matter how exactly I change them, no matter, so it should be representing the specific, so let's say king, queen, side castling, it should represent the specific number respectively. Obviously we would be debugging this during when we would be updating incrementally, when we would be incrementally updating our hash keys within the make move function. We'll double check this for sure to make sure it actually works. So let's go back to the initial stuff. Okay, and now if I change the side, so nothing has changed within the position, but I've changed the side, and the hash key should get changed as well. Okay, and it does get changed. Perfect. So the hash key is getting changed because we have changed the side. And the very last thing, well, it won't really tell you much, but just to give you an idea, that if we just, let's say, take the pawn away, then the key should get changed as well. So we just took the pawn away and the key has changed. So that's kind of it. Well, okay guys, so let's drop back to this tricky position because it's nice to test not only the move generator in regards to generating moves, but in regards to this to the debugging of incremental updates of our hash keys as well. And well, if I did everything correctly, then this should be the hash key for this position, the right hash key. I don't really remember which one I had when I did this in previous. Well, it doesn't really matter that much because well, just forget that. So most likely, if you did reproduce the steps I've made in this video, most likely, well, you should have the same hash key in this position. If you don't, that's the reason to get worried, because something has gone wrong. Okay, so I will also well, okay, just hold on a sec. Let me check if the generate hash key is actually implemented correctly, and if it is, then we'll end this video. If not, I'll fix this. So hold on a sec. Well, it seems like it is working, so if any troubles to face further on, I will let you know. So, well, okay guys, so this is it regarding this video, and starting from the next video, something really interesting and intriguing is gonna start happening, because we would be incrementally updating this hash key every time we move a piece or change the site, or if an peasant is changed or castling rights is changed. So this is really complicated, and it's not really that complicated to implement, it's complicated to debug. And I would also find the exact help that I had on Talk Chess and give credit to the guy that actually helped me to set up this framework that I would be using in the next video. So just to give him a credit. And yeah, the next video would be quite pretty intriguing, because I would be doing this in the live mode. So what I would be doing is actually comparing the incrementally updated hash key, like incrementally updated by hand, where manual XORing of elements, compared with the generated hash key from scratch. And now you might wonder, like, what's the reason for this incremental updates when we can just rebuild this hash key from scratch every time we make a move and then just take it back and that's it? Well, we can do that, and that was my initial intent. But when I did ask this question on Talk Chess, guys told me that this is really a bad idea because it would violate the performance quite pretty significantly. And when I've seen this with my own eyes and realized that my mood generator is getting so slow that it's just slow as hell, that in that time I've realized that it's really a good idea to go for these incremental updates, even though it takes some extra work to do. So we would be doing these incremental updates just to avoid slowing the performance of our mood generator down. So that's the idea, because otherwise all our improvements that we got from using bitboards would be just they will gone. That's it. So that's not what we want to achieve here. Well, okay, so this is it from my side. I hope you learned something interesting out of this tutorial. I hope to see you in the next one. Until that time, and take care.